Modern data centers must host and support an enormous variety of highly diverse applications, ranging from cloud services and streaming platforms to artificial intelligence systems and real-time data analytics. This variety brings complex challenges from a resource management perspective. In fact, each type of application has different requirements in terms of performance, latency, memory, and energy consumption. Traditionally, data center optimization has focused primarily on performance, but today it is increasingly necessary to also consider the energy impact of running applications. An intelligent management of energy consumption not only reduces operational costs, but also helps improve the overall sustainability of data centers. In this context, energy management at the hardware level becomes a crucial tool. These techniques make it possible to dynamically adapt energy consumption to actual computational needs, maintaining a balance between efficiency, performance, and reliability. In this lesson, we will delve into the main hardware techniques for energy management in data centers. We will see how these solutions allow for flexible and sustainable management of different workloads, representing one of the most widespread approaches in green IT. One of the most widely used techniques for managing energy consumption in data centers at the hardware level is dynamic frequency and voltage scaling. Dynamic frequency scaling, or DFS, is a technique that dynamically adjusts the processor's clock speed based on the context. A higher clock speed allows for better performance, while a lower speed results in reduced energy consumption and less heat generation. Dynamic adjustment makes it possible to lower the frequency when the CPU is idle, that is, when there are no computations to perform, and to increase it when the computational load is higher. The goal is to reduce energy consumption without impacting performance. DFS can be implemented through algorithms operating at the operating system or processor level, which monitor the CPU workload and adjust the frequency accordingly. Dynamic voltage scaling, or DVS, works in a similar way, but acts on the intensity of the current supplying the processor. The two techniques can be combined, often collectively, under the name of dynamic voltage and frequency scaling, or DVFS. The main advantage of these techniques is that frequency and voltage can be changed very quickly, allowing for a rapid response to changing workloads. However, the adoption of these techniques also involves some disadvantages. First of all, it increases the complexity of the system architecture, since it requires the integration of additional hardware components, dedicated software, and sophisticated control algorithms to dynamically manage frequency and voltage. Moreover, the continuous switching between different frequency and voltage levels can introduce operational overhead and negatively affect the stability and reliability of the processor. Under suboptimal conditions, this can cause timing errors, frequency fluctuations, and electrical disturbances, with a negative impact on the overall performance of the system. Another critical aspect is related to actual energy efficiency. If the CPU slowdown is not properly calibrated, it might reduce instantaneous energy consumption, but significantly increase the time required to complete a task. Since the total energy consumed is the product of the power drawn and the execution time, an excessive increase in duration can lead to higher overall energy consumption, negating the expected benefits. Power capping is a technique used to artificially limit the maximum amount of energy that can be consumed by a hardware component, such as a processor, a server, or an entire rack. This strategy allows for more efficient management of both energy consumption and heat production, keeping power draw within predefined thresholds. In this way, consumption spikes that could overload the electrical infrastructure or cooling systems are avoided, reducing the risk of failures, instability, and damage to components. Power capping can be implemented at two levels, hardware and software. At the hardware level, some modern CPUs have built-in power capping features that can be managed through power management tools. At the software level, power consumption can be controlled through operating systems, hypervisors, or dedicated tools. Manufacturers like Intel and AMD provide interfaces such as RAPL, which stands for Running Average Power Limit, allowing dynamic monitoring and adjustment of processor energy consumption based on workload. The advantages of power capping are numerous. In addition to limiting power consumption and heat generation, thereby reducing cooling requirements, this technique also enables more prudent energy management within the system. For example, it is possible to assign a specific energy budget to each component, preventing any single one from monopolizing resources at the expense of the others. This is particularly useful in data centers with shared infrastructures or those subject to energy constraints. However, power capping, nevertheless, also has some disadvantages. Limiting the available energy can lead to reduced performance, especially when dealing with intensive workloads. Furthermore, allocating the energy budget requires careful planning and a deep understanding of workloads to avoid inefficiencies or bottlenecks. Finally, not all processors or hardware components support power capping, and its implementation can vary significantly between different architectures. Another hardware approach involves the selective deactivation of unused components. Sleep states or C states are increasing levels of power-saving modes that processors can enter when they are idle, with the goal of reducing energy consumption and heat dissipation. They are provided by most modern CPUs and allow portions of the processor to be put to rest when they are not needed. The deeper the sleep state, the greater the levels of inactivity and energy savings. Sleep states are managed by the operating system and hardware, often through ACPI mechanisms, advanced configuration, and power interfacer, other mechanisms that allow dynamic switching between states depending on the workload. Entering and exiting deeper C states involves a certain latency, which can negatively affect performance, especially in applications that are sensitive to response time. For this reason, although the use of C states is generally advantageous in terms of energy efficiency, in some scenarios it may be necessary to disable the deeper states, especially when optimal performance is required in applications where low latency is critical. All the hardware techniques described are even more effective when integrated with intelligent energy management systems that monitor server usage in real time and dynamically adjust processor frequency and voltage, power caps, and sleep states. The adoption of algorithms based on artificial intelligence has led to energy savings of up to 40%, both in terms of cooling and computational load management.